So first example, you want to compute the line integral where this is your function and C is your line segment. So whenever you have a line, the easiest way to parameterize it is to just follow this formula. So you always do 1 point plus your variable times your other point minus the other point. So like kind of like a slope, but not really a slope. So if we choose this as our first point, 0, 0, 0, plus t times this line segment is from the point P1 to point P0. So you do 1, 1, 1 minus 0, 0, 0. So you do the endpoint minus the beginning point. And so this parameterization will give you t times 1, 1, 1, or you can write it as t, t, t. So whenever you have a line and want to parameterize it, follow this formula. Next step, so we've parameterized our curve and we just followed the line integral formula. So that says we want to do the integral of your function where you plug in the parameterization times the length of your derivative of the parameterization. So let's see what that is. So we want to do the integral from a to b. Well, they tell us, well, what is the lowest, like our parameterization is t between 0 and 1. That's because our lowest point is all zeros, our highest point is all ones. So our integral is going to be from 0 to 1. Our function is x minus 3y squared plus z. We plug this parameterization into our function. So let me write f of t for now. And then we do the derivative of our parameterization, dt. And so when we plug in t for our function, we have t here minus 3t squared plus t. So I just plugged in t's for all those variables. This is going to be the magnitude of 1, 1, 1 dt. And so that gives you 2t minus 3t squared. This length is 1 squared plus 1 squared plus 1 squared. And so you get square root 3 of 0, 1, 2t minus 3t squared. Then move the 3t to the front. And then you can take the integral as normal. You'll find that you get 0. Yes.
So I know it probably didn't matter here, but like when you say the magnitude of the derivative, I was under the impression that you kind of did the dot. Is that would that be wrong?
It's not really the dot product. So you take the derivative of your parameterization. So that's 1, 1, 1. And the magnitude is you're doing like, oh, what I wrote here. It's not really a dot product. Yes.
So I think these are the same thing. Would you do the dot product if you have multiple equations? Like with last unit when we did the dot product for the magnitude, that was because we want to parameterize 2 different equations. Is that why? Is that what it differs?
I think we just integrating over the scalar field. Or not over, like your function is like a vector field instead of a scalar.
Yeah, it might be for later when we do. Wait, we're in scalar, right? Yeah, wait. Dot product. So when you say dot product, that was for like surface integrals.
I think that's the cross product that we use.
I think we use dot product
Some last week we found like the magnitude of the cross product or like something.
Yeah, for surface integral. So we had like some like function and we did like the derivative cross product, some other like derivative. So that's a different formula.
Okay.
Yeah, that's the formula for surface integral. Yeah, where the variables are. Yeah.
So choosing the bounds, like how do you go about choosing the bounds of the integral after you parameterize it after, like when the points are like equal, like 1, 1, or 0, 0, 0?
So okay, so wait, let me see if I have. Let's do this example and see what we end up with. Okay, so this is practice problem number 3. So it says compute the circulation. Okay, wait, actually this is a circulation question. Okay, let me just explain it back to here then. So like t is gonna be like however you parameterize it, what's the smallest value of t and whatever is the largest value of t. So like even if your parameterization was 0t, 2t, you want to make sure you choose a t so that you're not like going over points or going under points. And specifically for a line, say this was your line. This is 2, this is 2. Then the parameterization would be t comma t, where t is between 0 and 2. Because x value can be any t from 0 to 2, y value can be any t from 0 to 2 also. If this was 3, then it'd be a different parameterization actually, because now the slope is not 1. So the parameterization wouldn't be tt anymore. You would have, so x, so you can choose x. If you choose x to be, okay, wait, sorry, what is this line? Y equals 2/3 x, right? So if we choose x as our t instead, y is 2/3 t. We see that we can still choose t is now between 0 and 3. Because t, if we put 0, 0, that's at this point. If t is 3, we get the point 3, 2, which is this point. And so that's how you would choose. Any other questions on this problem? Yeah.
Would it be easier to like just write everything in line and then do that, or like put it into that formula?
Either works. Yeah. If this is like simpler, like where you can find the equation of the line, then yes, this would work. But if you're given like some weird 2 points or whatever, maybe this also works. Okay. So then we have additivity. So this is where you have some large curve, but it can be broken up into different parts. So if you have this curve that can be broken up to like C1, C2, Cn, meaning like if you have, this is like your first curve and this is your second curve, then we can find this line integral over both curves by doing them separately. So you can first do the line integral of C1, then do the line integral of C2 and add them. So for example, if you have this function and we see that our curve can be broken up into 2 line segments. So C1 is this first line segment from 0, 0, 0 to 1, 1, 0. C2 is our second line segment from 1, 1, 0 to 1, 1, 1. So how do we do this? First, let's work on C1. We parameterize it using the formula again. So we have 0, 0, 0 plus t times P1 is 1, 1, 0 minus the first or the 0.000. So that's our first parameterization. For our second parameterization, we do the same thing and we end up getting 1, 1 t. Then we use additivity. So using our parameterizations, we plug into our formula. So you have the integral of f ds, where f, you want to plug in your parameterization times the magnitude of the derivative again, dt. And we do the same thing for the second curve. And we can simplify and get our final answer. Any questions on how this concept works? Okay, then let's do this example as, actually no, this example is fine. Let's skip it. So let's just do a definition. So for a curve, you have the arc length is 1 ds. So we just saw before that we were doing the integral of like f ds. But if you just wanted to find the arc length, you have 1. And so just a quick recap of everything we've done with including ones, we saw that the area would be if we did the double integral of 1, volume was triple integral of 1, surface element was the integral of 1, arc length is what we're now doing, which is the integral of 1, yes. Okay. Any questions before I move on to vector fields?
CDS means like art.
No, DS is like this formula. So you plug in the parameterization f and the magnitude of the derivative. This part is DS. Okay. Also, I think I messed up those forms. That should be scale. First one should be scalar. Second one should be vector. Okay. Okay. So then we have line integrals over vector fields. So, okay. So a vector field is some function over some domain, and it's usually written in the general form of this, or in a different language now. There's the one form language. Given some vector field, the associated one form field is written like this way, where you have like the dx's. So the one form way has the dx's. The vector field way just has like function with variables. And we can sketch what a vector field looks like. So let's do one sketch. So I'll do this example and I'll let you guys do the second example. If we have this vector field defined by cx, cy, where c is greater than 0, what would the vector field look like? Well, in order to do that, we have to, the best way I think is to kind of test points at first. So imagine that we're trying to find what is the vector at some point 1, 1. This is like 1, 1. So we would plug in 1, 1 to f, and we get c times c. Pretend c is like 2 for now. So we get, actually, let's pretend it's 1. So we get 1, 1. So that's a vector that looks like that. What about if we tested a point like 2, 2, then our vector would be 2, 2. So at this point 2, 2, we have a longer vector of length 2, 2. If we test a point over here like 0, 1, that's this point, then we would get 0, c, which is 1. So we have this blue vector here. And if we tested 0, 2, we get a longer vector. And you'll notice a pattern that it looks kind of like a firework. And so this will be our vector field. There's like a bunch more vectors here. But. Okay, so this is called uniform expansion, because you can see that it's like expanding outwards and it keeps getting bigger and bigger and bigger. Okay, what about this second one? Does someone have an idea of what this would end up being? And you can try to test out points and see like what it looks like. Yeah, so it's going to be a rotation one. And so you can keep testing points. So like, for example, f of 1, 0, where c is 1, you'd get -1, 0, wait, sorry. This is cy, so this is 0, and this would be 1. So at the point 1, 0, you have a vector that goes 0 in the x direction, 1 in the y direction. Then at 0, 1, you have -y, so -1, 0. So this is 1 negative in the x direction and 0 in the y direction. And you can keep going and you get this kind of rotational shape. And so this is uniform clockwise rotation. Okay. Questions on those? Yep.
The sign on the other one would like to be clockwise, or how do we determine?
So yeah, so if the sign was on the other one, so like y -x, then at f of 1, 0, you get 0, -1. So it'd be 0. Yeah, it would be clockwise. Yeah. Okay. Any other questions on this? Okay, so then we have the gradient vector field. And so that's given by the same, kind of the same as what we've learned about the gradient before, where we're taking the derivative. Just now we have lots of more parts. So in general, this is our definition. Or you'll see in the green, I'm always writing like the one form language in green. So if you wanted to write it in the one form language, you would have this gradient vector. The associated one form field is this, the gradient vector field times dr. Or specifically, we see that we have all the like dx's again. And this is called the gradient one form field. Okay. So let's do, let me see. So now we're dealing with vector fields, right? So in general, if we have some parametric evaluation, we see that, oh, actually I did write it correctly. It is still the first one. Okay, we have this definition again. But now the only difference is F is some vector field. And so we have this same definition where we have F dot dr is you plug in your parameterization into F, do dr dt, ln dt. And there's an n equals 2 case and an n equals 3 case, depending on how many variables you have. So let's do an example of that. We want to compute the line integral where f is this and c is your curve or path given by this parameterization. So the first step is always to parameterize. We're already given that. Second step is to use the formula. So this is our formula. A is 0, 1 is, B is 1, because that's our t bounds. We take our function and we plug in our parameterization. So if we plug in our parameterization, we get square root t, because that's z. Xy is going to be t squared times t. Y squared is going to be t squared. That's our function with the parameterization plugged in. Then we take the derivative of our parameterization. So that derivative is going to be 2t, 1, and 1 over 2 square root t, dt. And so this gives us 2, let's see, if we dot product it, we have 2 t to the 3 halves plus t cubed minus a half t to 3 halves dt. Okay, and then you can take the integral as normal to get 17 over 20. Any questions on, yep,
Right, just because, so this is the vector, like in the vector field, so that's why we're doing the dot product. If it's a scalar field, we don't use that.
yes. Oh, yeah.
Right.
Yes, so this is, yeah. So because this is now a vector field, whereas previously we had this scalar field. So F was given like as F of X, Y, Z equals this, whereas scalar field, now we have, where am I? Now this is a vector field, so like a capital. Okay. Wait, what was this about? Let me just check something. Yeah, okay. Okay, but actually, if even though we're still over vector fields, our functions could be scalar functions. So we're over vector fields now. What we just did was if our function was a vector, we do the dot product. But if our function is a scalar, now it's this definition. Where now we also still do the dot product, but our functions and our like differentials are just written differently. So over the vector field, yes, you do dot product. So for example, now we have this, if we have our function is a scalar function, we're still over vector field, but we have scalar function. Then we have our curve, we always parameterize it first, and then we plug in our definition. So our definition for the, they usually occur in like, you have multiple like dx, dy, dz, etc. But for the n equals 2 case, you have some m with your parameterization plugged in, dx, plus n with your parameterizations plugged in times dy. So let me give an example. So in the last example, we had a function in the vector form. So we had f of x, y, z equals like x, 2x minus y, whatever. Now written in the scalar form, it would be written like mnp equals something. So notice that there's not like a function, like we're not plugging things in to get an output. Now this is written this way, like m is negative y, n is z, p is 2x. So if your function, your function is given this way and you have a curve, we want to compute this integral. First step, parameterize. They already gave it to us. Second step, use the formula. So the formula says we want m, and we plug in our parameterization. So m was negative y. We plug in what was y, that was sine of t. So we would plug in sine of t. Then x was cosine t, so, negative y. X was cosine t, and we want to take the derivative, so that's another negative sine t. Plus n, which is our second value, or z. We plug in our parameterization, so z was t. And then we take the derivative of y. So derivative of sine t is cosine t. Plus, our last term is 2x. X we said is cosine t. So that's 2 cosine t. And then the derivative of t is just 1. So you would have in total this integral. Okay, and t is 0 to 2 pi. So 0 to 2 pi. Any questions on how that works? Let me scroll it up so you can see everything. Okay, so in summary, we have the line integrals and we have two forms, vector form and the scalar form for over vector fields. Okay, and that summary is included here. Okay, I also wrote out a nice chart where you have line integrals like the scalar version and the vector version, what the differential elements would look like probably, because you've probably seen there's like lots of different ways to write stuff and they end up being the same type of problem. So for scalar version, the integrand would be like some function. Vectors, we know they're written like this way. How to solve it, they're solved very similarly. Here, I made the distinction. Scalar is where you just multiply by the magnitude. For the vector version, we do the dot product. And actually, the reason we do the dot product is because here we end up getting a vector, and here we get a vector, but we need to have it as like a scalar or like a number in order to integrate it. So that's why we dot product it. Yeah. So this is a nice chart. Okay, any questions before I move on to applications? For flow and circulation. Yeah.
How is it distinct again from like the scalar form?
So in the scalar form, so okay, let me scroll. So a scalar function. Wait, let me think about. Okay, let me see. So here in the scalar function version, we're given like this is a function where you input x, y, z, you get one output. So that was at the very, very beginning. But then the last question we did over the scalar over a vector field, with a scalar function, you should be given like this would be like one expression, like m is negative y, n is negative z. So it's different in that now you will have like the x, dy's, and dz's, whereas in the other one, we were just doing the derivative of the parameterization as a whole, like together. Yeah. Oh, yeah. I'll think more about that. If I come up with something, I'll post on Piazza. Yes.
And then like another stat, and then there's the like the idea of like being the vector field or scalar field. Is that like what are you?
So in general, like the idea is always the same. You're plugging in your parameterization into the function, multiplying by something. The only difference is going to be what you're multiplying by. So, okay, let me vector. So a vector field is going to have each thing itself is a function. So let me think. So yeah. Okay, wait, back to this. This goes into this chart then. So like if you're given just like a regular function, lowercase f, that's like the scalar version, whereas a vector version should give you like an I or j, or it can be written like an actual vector, or it can be written like dx is dy. So that's how you tell if it's going to be a vector version or scalar version. Okay. Any other questions on that? Okay. Let's do some quick applications. So here I just explained like the definition. So if F is a force field, then this line integral that we found is going to be the work done along your curve. If F is some velocity field of some fluid, for example, then this integral is going to be the flow along C. And then furthermore, once you have the flow, if your curve is a loop, so it's not just like a normal like curve, but it's actually a loop, then it's called the circulation. And a loop means that it should start and end at the same place, is the definition of loop. So if you wanted to compute the flow of this, the flow where your function is given by this, and this is your curve. Well, first, we always see that we've done the parameterization first. So the parameterization they gave us. Second, we follow the formula. So here we're dealing with vectors. So we're going to follow the vector form definition. Oh, did not mean, oh, okay. So then we have our function and we plug in the parameterization. So x is cosine t, z is t, and then y is sine t. Then we take the derivative of our parameterization, dt, and you can compute the integral and get this answer. Yeah.
Is flow just like work? Or is that the flux?
Flow. No, flow is not the same as work, but flux is a different.
Oh, so flow makes sense.
Yeah.
Okay.
Okay. No, flow is separate from flux. Let me. Yeah. Okay, so this is just in general, you have a capital F, you have work, flow, circulation. If your curve is a simple closed plane curve, so like it's closed, then given some function, now we have circulation and flux. So circulation is going to be this like simple thing, m dx and dy. Flux is going to be m dy minus n dx. So notice the differences here are that the x's and y's flipped. And here you have a plus, here you have a minus. So circulation and flux are very similar, but the formulas are a bit different. And circulation kind of, I put like a little interpretation here. It measures the tendency of your vector field to flow on some curve, like to flow in the same direction as this curve. Whereas flux is the overall tendency of some vector field to cross like a curve. Okay, so let's do an example where we're trying to compute the circulation and the flux. So we're given some capital F vector function. The first thing, the first component, we're going to call M. The second component, we're going to call N. And our curve is this, what is this? A circle, right? So step one, parameterize. Step two, follow the formula. So for circulation, the formula is mdx plus ndy. So we have A is 0, B is 2 pi, because that's our bounds. M is x minus y. So we want to plug in our parameterization. So we have x, that's x, minus y. Y is sine t. The derivative of x is negative sine t. Plus, now we have n. So n is going to be x cosine t times the derivative of y, that's cosine t, all dt. Okay, and I will also leave the integration. It will be 2 pi. For flux, we have a slight difference now. So now it's still 2 pi, 0 to 2 pi, but m, so m is x minus y, right? So it's still going to be cosine t minus sine t. But now our dy should be cosine t, because y was sine t. And then minus, this is still cosine t because it's just x. But now the derivative of x should be negative sine t dt. Okay, and that will give you pi. Any questions on this example? Yes.
Was it always the
C dt.
like 2D?
Oh, I think most often, yes, but let me see. Do I have a 3-dimensional? There might be a 3-dimensional in the practice problems, maybe. Or no, I think it's usually 2-dimensional. Okay. Any other questions on that? Okay, so since our recitation is now like an hour and a half, let's take a 5-minute break in between. So let's do a 5-minute break ending at like 2:33, 6 minutes. Maybe I should stop the recording. So recording resumed. Okay, so next topic is conservative fields. Okay, so F is, if you're given F is some vector field, then F is conservative on some domain if your line integral is path independent. So what this basically means is that if you have two different curves, then it doesn't matter which path, which curve you take, your line integral should give you the same answer. So this is what it's saying. Like you have C1 curve, C2 curve, they should be the same. In the vector one form language, it would look like this in the green. So then we have the very important theorem, the independence of path theorem. So that says that if you have a continuous derivative in your domain with boundary points A and B, so you have some starting point and some ending point B, then what this theorem is saying is that when you do the integral of the gradient.dr, you can plug in your endpoint to your function minus your beginning point into your function. And in the one form language, it's written like the green. Special note is that if they give this to you as like a gradient in like the gradient form, don't just take that gradient and plug in like your B and your A. You need to find what this function f is. And I have an example at the very end of finding f. So yeah, okay. And just a note that like this f, once you find it, the f is usually called a potential function. Okay, then we have this corollary. So it says that the gradient integral is path independent. So if your function is this gradient, then we can say that f is conservative on your domain, or that like f is path independent D. And knowing this, knowing that f is conservative on D, that only happens if and only if your f is your gradient on D. So that's just restating our corollary in an if and only if way. So let me do an example. So we have this, we want to compute this, and we're given the potential function already. We're given f is this. C is some curve from 1, 0, 0 to 0, 0, 2, and it doesn't pass the origin. Then how would you evaluate this integral? Well, because you have some starting point and an ending point, by the fundamental theorem of line integrals we just had, you want to evaluate f at your end point minus f at your beginning point. And since they already gave us our, yeah.
That's probably the corollary that you were talking about.
Yeah.
So is it the only time that it's path independent is when you're working with the gradient?
Let me wait. If it's not path, yeah, because by the if and only if you're saying that f is not conservative, then you just can't say that it's definitely a gradient. So this is like if it's conservative, then it's a gradient, or if it's a gradient, then it's conservative. Is what the if and only if.
But it can be conservative and not a gradient. Or that's part of the definition of a gradient. The gradient is a path independent.
Let me see. Or I think it might be possible. Yeah. Okay, so we have this function, and now we just plug in 0, 0, 2 to our function. So we have -1 over 0, 0, 2 minus -1 squared, 0 squared, 0 squared. So that gives us -1/4 plus 1 or 3/4. Yes.
What is?
So it has to do with like the tangent line, or yeah, the tangent. I believe there's a prep quiz question on it. Like prep quiz. Let's see. Let me think about. Oh. Actually, it's not on here. Okay, never mind. Oh, if it's a level set, then y is this like one form 0. So it has to do with like the tangent vector and like your gradient. So your tangent vector to this level set gradient is always going to be 0. So wait, let me get back to your original question. Why does it have to be the gradient? Potential function for curves. So yeah, I think it has to do with the gradient in order, it has to be a conservative so that you can like follow this independence of path theorem. Okay, yeah, let me get back. I'll get back to you on that. Okay. Any questions on this problem? Then we have the component test for conservative derivatives. So in order to make sure that it is conservative, we have to test certain criteria. So we have to check that the partial of f sub I over the partial of x sub j is going to equal, like we flip the indices. So partial of fj partial over partial xi. And so if we check that this is true for all I not equal to j, then we can say that f is conservative and it's going to be the gradient. So let me do an example of this conservative test. Okay, this question. So determine whether f is conservative over its natural domain. If yes, then find a potential function. If no, then don't find a potential function. Okay, so by the component test, we have to check all of these expressions for all I not equal to j. So what does that mean? Our function is given like this. Let's call this is m, this is n, this is p. So we need to check all different combinations. Well, we have if I is 1, j is 2, then we would be checking a 1, 2, 2, 1. If I is 1 and j is 3, that's another possible combination. The last combination is if I is 2, j is 3. By checking these three things, we've checked all possible combinations of that we need to check. So for the first one, what does I equals 1, j equals 2 mean? That means we're doing the partial of the first thing, so that's m, over the partial of the second, like x, y, z, so that's y. Is that equal to, now we do the partial of f, the second value of f, that's n, over the first value of our variables, which is x. So we need to check if this is equal or not. Well, what is m? Well, m is this thing. If we take the partial with respect to y, we're left with e to the x plus z. Wait, e to the x, sorry, sine y plus z. This term, partial of n with respect to x, that gives us z minus e to the x plus e to the x, minus, oh, there's a negative sign out here, minus e to the x sine y. And indeed, they are equal. So we've checked our first criteria. Second criteria, I equals 1 and j equals 3. That's saying is the partial of m over z equal to the partial of p over x. P is our third thing. And so we can check that. What is the partial of m with respect to z? Well, there's only one z here, so that's y. P is this term. There's also an xy, so the partial is y, and they are equal. And the last thing we check is partial of n over z. Is that equal to partial of p over y? Well, we get x equals x, so that's also true. So by checking these conditions and that the fact that they're met, we know that capital F is conservative over its domain. Any questions on, yeah?
So, only like you do it in, so you do it in pairs, you don't do like all of them equal to each other?
No, so you do it in pairs. So like you want to match the I. So like do this one first with some I and J, and then do it again with some other I and J. Okay, and yeah, the point of that is that you just need this, the yellow, to match the green. Like you don't need the yellow to match this red one. So that's why you have to do it in pairs together. Okay, so now we know that it's conservative. Let's try to find the potential. Oh,
I equals 1, j equals 2 to those parts.
so I wrote down like our like components of capital F, which are M, N, and P. And then we have, what are all our variables? It's X, Y, and Z. So I choose this as like anything with 1 will be like an M or X. Anything with 2, anything with 3. So I being 1 means that we want the first thing of F, so that's M. Then J being 2, we have X sub 2, so we want the second variable, that's Y. And then it should equal, this would be the partial of F, J is 2 over X1. So the second F component is N, the first X component is X. So they're kind of going like in opposite directions. Okay, let's find a potential function. So there's 2 methods. First method is to kind of like guess and check a little bit. Second method is to actually try like taking the derivative, integrating, etc., but it's a bit more involved. So let's try the first method first. So this is what we know. We know the partials right now. We know partial of F with respect to X, with respect to Y, and with respect to Z. We're trying to find some F, lowercase f, X, Y, Z, so that if we take the partial with respect to X, we get this. Partial with respect to Y, get this, Z, get this. So if we have this first thing, let's take the integral with respect to X, right? Because we did the derivative, but now we want to undo it. So let's take the integral with respect to X. We get e to the X, let me do it in orange also. E to the X cosine Y, because the integral with respect to X, there's just that 1x. This is a constant. Plus, now we have a YZ X. Because if we took the derivative, we'd just be left with YZ. Plus, we have some other term that might only have Y's and Z's. Because that way, when we take the derivative with respect to X, it becomes 0. So this term disappears when we do the derivative. Now we do the same thing for this second term. So F should be, if we take the integral with respect to Y, we have xzy plus, what is the integral with respect to Y here? Well, that's going to be e to the X cosine Y plus some other term with just X's and Z's. Because when we take the derivative, it disappears and it's not in our expression anymore. Then this last thing, so we take the integral with respect to Z. So what do we get? We get an XYZ plus, here's the Z, so integral is 1/2 Z squared. And then plus some term with only X's and Y's. So can anyone guess what our function F should be based on this? Yep, plus 1/2 Z squared. Exactly. So we found our function, and notice how I color coded it. So like once you take the integrals, we want to see if we notice any patterns. Each of these has an X, Y, Z, so we know that has to be in our F. We see 2 oranges matching, so this orange must also be e to the X cosine Y, and that must be an F. Then we have the red is what's left, and so that must be an F also. And so this is our potential function. You can add a C, because whenever you integrate a constant, it goes to 0 anyway. So you could add a C for some constant C. Okay, any questions on this method? Yes.
So it's a question about finding the partials again.
Finding the potential function.
Oh, no, I mean the partials.
Oh.
It's I and J.
Oh, yeah, yeah.
It's, I'm kind of confused because like I was looking at the line, like with each one.
Mm-hmm. So like, yes, so, okay, so we have this first one is I goes 1, J equals 2. So like the other one you're thinking of is what if J equals 2, I equals 1, right? But then what is I equals 1, J equals 2 mean? That means we're doing F1, X2, and we're checking based on this, is that equal to partial of F2 partial X1? If we did this thing, what would that be checking? That would be doing F2 with X1 equals F2, sorry, F1 over X2. Wait, am I missing it? 1. Oh, I wrote the same thing here. Sorry, this should be J equals 1, I equals 2. Let me write it in the same order so we're not mixed up. I equals 2, J equals 1. Well, then that would be partial of F2, X1, partial of F1, X2. But we see that they're doing the same exact thing. They're both checking if partial of F2 with X1 is equal to partial of F1 over X2. So it's kind of like repeating. So we don't have to redo this one again. So that's why there's only going to be 3 choices. Okay. Then the second method for finding the potential function, this is like more work and it takes a bit longer, but it's also more like rigorous if you want a rigorous way. So if we start with one of our first partials, this partial with respect to x, we can integrate it and it'll give us e to the x cosine y plus xyz, plus we know it has to be something with y's and z's, because then when we differentiate it, it becomes 0 and we don't see it in our expression. So temporarily, this is our function in green. Then we differentiate it with respect to y and see how does it compare to what we already know about y. So if we differentiate it, we would get this negative e to the x sine y plus xz plus the partial of this with respect to y. So let's compare this purple and the purple. Well, we have an xz already. We have this e to x sine y. So really this partial is just 0. We don't need it according to comparing our purples. So if the partial of this should be 0, and that means that g could be like some constant, but let's not write that for now. Then what about if we differentiate our green, our original function, with respect to z? And let's compare it to what we know about dz. So now we're comparing this purple and we're going to compare it to this purple. So I took our original function, which is in green, and took the derivative with respect to z to get this. What is our z that we know? It has to be xy plus z. We already found that. So comparing it, that means that this partial of h with respect to z, so our like extra function, has to equal z. If that's true, when we integrate it, we get that h is a half z squared plus a constant, because when you integrate, you always add a constant. And so now we found what our function is. We continued the green thing. Our green thing said it was e to x term plus xyz plus some g. And we just found that our g has to be half z squared plus z. And so this is our final function. So we get the same answer using the guess and check way or this way, just whatever works better for you. Any questions on that? Okay, one last question. So this is practice problem number 23. Okay, So we're considering the one form field on R cubed, which is given like this. And my first question is, show that this function, this alpha, is a gradient one form. So what should I do in order to try to see that alpha is a gradient one form? Any suggestions? Yep, because that's the component test, right? The component test, by checking that all our like criteria meet, then we find out that it is a gradient one form. So if we do the component test here again, because you can think about this as like M and P, and we have three variables, X, Y, Z. So we again test three things, three equalities. Are we checking? We're checking this, this, and this. Okay. And you'll see that all three of them do match. So they are, it is a gradient one form. Then my next question is what the question is actually asking. What is the integral of alpha along the clockwise, counterclockwise unit circle in the plane? Okay, so think about this for a second. And my hint is going to be that you don't need to calculate anything. Think about what should my alpha be? Or like integral of alpha, sorry, not just alpha. Yeah, it's 0. So the reason it, and do you want to explain why? Yep. Yes. So what is the integral of alpha? Well, we know by the independence of path theorem, which I mentioned earlier. So by the independence of path theorem, and it's also like kind of using the fundamental theorem of calculus a bit. Fundamental theorem of calculus, which was a long time ago. We know that the integral of alpha is 0. So by this. And the reason this is because our curve is a unit circle. They're saying that what is the integral of this along some curve, this unit circle curve. The unit circle is a closed loop. If it's a closed loop, that means your ending point equals your starting point. So when you're doing the fundamental or the independence of path theorem, we always do like f of the endpoint minus f of the beginning point, but then they're equal. So that gives you 0. So this question, if you try to actually like compute it, it might take a while. So the trick was to recognize that it's a closed loop. So this integral is 0. And I also explained like a quick summary of it here for why it's 0. Yes.
So if your function wasn't a gradient one form, wouldn't you be able to do like the trick?
Yeah. Because the independence of path theorem only works if it's like conservative or like if it's a gradient. Yes. Yes. Okay. Any other questions on this problem? Mhm. Yeah. So like if one of these didn't work, then that means it's not a gradient one form. So you can't just use this nice trick, this theorem. Yes.
How is that like a circle if it has a spherical element?
Circle. So the only thing we have to check is what is this curve? The curve is a unit circle. So remember, we're always doing the integral of something along a curve, like an actual like path. And so this path is itself like a curve, this unit circle. So like think of just a circle. And so the starting point is the same as the end point. Okay, any other questions on this? Okay, if not, I'll open it up to other questions? Because that's the end of my notes. That's actually finished on time. Okay.